Hello and welcome. In this video I'm going to speak about data center bridging. I'm going to give you an overview of this feature, and I'm going to tell you that OcNOS of course supports this feature so that you can use it in your data center environment. This comes after our quality of service discussions and the number of queues and how the queues are treated in OcNOS that I have spoken in previous videos. If you have not checked them, I highly recommend you take a look at those videos. But here what I'm going to show you that data center bridging is going to kind of combine the storage network and the Ethernet network that we have here, and we can just utilize one network to do everything in our data center environment. So this is a traditional data center topology. As you can see, I have my Ethernet network up here with different types of topology. It doesn't really mean you have to go with a specific one. For example, we have a fabric here which is designed with class topology, and this is, for example, my spines, this is my leaves, and down here of course are my servers. So this is going to be my Ethernet network. But on the other hand, servers have other types of network adapters which they can use to connect to storage area network. So up here we have Ethernet network, and down here we have our storage network, which means that the nature of these two networks are totally different. Ethernet network is lossy in nature. What it means is if the queues are full on a port on a specific switch, for example, then the rest of the packets that are received by the queue is going to be dropped. Or maybe we configure a threshold and we say, for example, beyond 80% full, then we are going to drop selectively or randomly all the packets that are being received in there, or some parts of the packets, of course. So which means that the traffic is going to have some packet loss based on the type of traffic. For example, UDP, we are going to see some let's say, I could say, for example, I'm going to lose some of the packets and I'm not going to be able to recover them. And of course in UDP we don't really care about recovering the lost packets, for example in a video or voice call. If this is a TCP transaction, then what is going to happen is the destination is going to send some acknowledgements and it's going to say that some of the packets are not received. Then the sender is going to be responsible for sending those packets again, and also based on windowing it's going to reduce the number of packets that are sent at the same time, and also reducing the speed of the transmission. So that is lossy nature of Ethernet network, and that's okay. We have no problem with that, and we have just done this ever since Ethernet protocol has been around. What about the storage? Storage is lossless, and we don't really think about those types of mechanisms to retransmit the data. We just assume that this network is totally reliable, and of course it is. And based on the medium that we use, for example, which is most of the time is fiber optic, based on the topology that we use in here, based on the devices and the proximity of the devices to the servers, all of them are going to help us to have this lossless network. And with that, we know that in case, for example, the buffers are kind of being full, then what we are going to do is we just ask the sender to pause, and then when the buffers are not full, then the sender is going to resume sending the data. You have seen this on your computer, as a matter of fact, just attaching to your hard disk. This is how the data is being written on the hard disk and read from there. But in a storage network, of course, in a SAN environment, lossless is very important. Now, what we are going to do here, we want to kind of combine these two into each other. And then we have a new protocol which we call it Fiber Channel over Ethernet. And Fiber Channel over Ethernet is going to treat both Ethernet packets and storage packets, Fiber Channel packets as a matter of fact, at the same time. And what we are going to do is to just make sure that this storage traffic is going to be lossless, and this Ethernet traffic is going to be lossy in nature, and we have no problem with that. So let's go to the next slide to see what we have here. So like I said, FCOA is going to merge LAN and SAN onto a single converged network structure. So what we are going to have is the amount of cabling that we have here, the number of ports that we have to utilize, and the type of ports, of course, are going to be different on the switches. The number of switches, we don't really need to have kind of those NDS switches in the network anymore. And the number of I/O cards, we have kind of converged network adapters, which we call it CNAs, which is kind of a network adapter as a matter of fact, but at the same time we can manage LAN and SAN cabling on this. And also in the end we are going to reduce the amount of money that we have to pay in our network, and of course the complexity of the network is going to reduce as well. So these are the benefits that we are going to have. Now data center bridging is going to come into play to help create this kind of a network in here. And there are some components for data center bridging. These components are going to be, as a matter of fact, 4, but in some platforms you might see a little bit more than that, based on the platform that you work on. But the standard ones, of course, are going to be this first one, PFC, which is going to kind of provide us some kind of a quality of service features in here. We have ETS, which reserves the bandwidth for us. Again, these two are going to work with each other. We have congestion notification, kind of sending the messages to the sender, and then tell the sender to pause the transmit, and then again we can just ask it to start resuming the transmission. And in the end, of course, there is a protocol which is going to negotiate all of these features with the other switches, and that is called DCB exchange protocol. So this part is very important. What I'm trying to say here is we have quality of service features on all of the switches on the way to the destination. Let's say that this is a leaf switch here, this is a spine switch here, and this is another leaf switch here, and I'm trying to kind of go through this to get to this server here, and let's say this is my storage, and this is a server which is trying to reach to that storage in here. This is L1, this is L2, and let's say that this one is S1. What is going to happen in this very simple topology? What we have here is the server is going to be responsible for slowing or increasing the speed of sending the transmission to the other side. These leaf switches, of course, all of them are going to have this quality of service features installed on them and configured on them, and which means that I'm not going to miss any of these links, because the type of traffic which I'm sending here, this is going to have a specific marking on that. The leaf is going to receive that packet with that marking. It's going to send it to the other switch. That switch is going to again care about the marking that is received, and it is going to treat the traffic based on the marking, and it's going to send it to the destination. And again, this leaf switch is going to have the same thing. So all of the switches on the way from the source to the destination, all of them are going to have this QoS policies installed on them, and all of them are going to treat the traffic as it should be. If one of these switches miss this kind of configuration, then the traffic which is received is going to be treated as best effort, which in this case, of course, is going to drop a lot of packets, and we do not really want this in our network, because we don't have any kind of retransmission or sequencing or stuff like that enabled on our SAN traffic in here. Once again, when we have this kind of a network, all of the responsibilities is going to fall on the sender. Sender is going to make sure that it's going to pause the retransmission, it's going to resume the retransmission, and it's going to take care of the speed of the transmission to the destination. The good thing is we don't really have to go for some new protocols to enable DCB. DCB, of course, most of the configuration is going to be the default configuration, so you don't have to do anything about the configuration. I'm going to show you some of the configuration in case you want to change, but the defaults are going to be totally okay, and you can just make some tweaks just to make sure that it is going to suit your environment in your network. But DCB is going to be part of LLDP protocol, which you already have it on your devices, so you can just enable that and use it. The devices are going to discover and learn each other using this protocol, and now DCB is going to be in place. Another good thing about DCB, based on this, you can of course tell what is very good about that. This is the vendor neutrality. That is because DCB is part of a standard, and almost every device that you have from different vendors support that. So this is not specific about OcNOS devices or any other type of devices. All of them are going to, understand DCB in here. There are some components for that. Like I said, I have just named them before, but you can just take a look at the right side and you can see some of the standards that are in place. PFC, all of them are IEEE standards, as you can see, as 802.1, QVB.1, QAZ for ETS, of course. Like I said, this one is for bandwidth reservation. DCBX, which is the exchange of the negotiation between the different switches. Some platforms where we have one thing which is called quantized congestion notification, but we just generally call it congestion notification or explicit congestion notification on this platform that we use it. And also some other components that in my case, of course, we are not going to use them. But you can just take a look at each one of them. All of them are built on the standards that are available in networking. Let's say. But each one of these, I'm going to just take a look at them a little bit in more detail. So the first one is PFC. Like I said, as you can see, we are going to allocate network resources based on the relative importance of different type of data within data center. PFC is kind of a marking mechanism in this case, of course. It's going to make sure that the classification is going to be done correctly. PFC ensures the critical applications or services receive priority access to available bandwidth. And it also allows classification or differentiation of network traffic, as I told you. The mechanism with which we do this is that when congestion occurs, PFC enables switches to send pause frames to upstream switches. And that's going to go and get to the sender. Once the congestion is subsidized, resume frames are going to be sent to the source of the traffic. So these are the benefits that we are going to receive through PFC. What about ETS? That's going to manage network traffic in data center. And the purpose is assigning the amount of bandwidth that is going to be used for this type of traffic. You can say, for example, on a general point of view, what I'm going to do is this. I'm going to say for Ethernet traffic, I'm going to allocate something like 50% of the bandwidth, and for SAN traffic, I'm going to allocate another 50% of the bandwidth. So I'm not going to, use the SAN extra bandwidth in case there is an extra bandwidth. I'm not going to allocate it to Ethernet, and this is kind of a reserved, and based on that, I'm going to use this for our SAN traffic. So that is what we are going to do in ETS. The operation, of course, based on some hierarchical scheduling algorithm. I'm not going to go through this in detail, but you should know that this is what we have in here, and we are going to share the bandwidth using weighted round robin. That is based on the importance of traffic that we have in here. And of course, SAN traffic is going to be marked specifically. Some network administrators prefer to mark this as COS3 or maybe COS4 based on this. This is just a tradition. You don't have to do that. You can say, for example, marking SAN traffic with COS0 or COS7 or whatever number that you want to have. And what is important is you have to keep this kind of uniform around all the switches that you have in your network. But these are the conventions that you have, and you can just use them and treat SAN traffic based on this. And the other COS values could be assigned to any type of Ethernet packet which is going through this network. And like I said, DCBX, of course, is the protocol to negotiate these values. So the configuration is going to be exchanged, and also the conflict resolution is going to be done between the devices using this one. And you should know that DCBX, like I said, is an extension of LLDP. As a matter of fact, we have a specific TLVs, type, length, and values, which are used for this kind of negotiation in our network. So that's an overview of data center bridging. And of course, let me just show you that there is a configuration guide in here. If I just go to IP Infusion website and go for the documentation, as you can see, we have the documentation separate for data center and also for service provider. In this case, I have opened the data center version. As you can see, it is docs.ipinfusion.com/datacenter. That is the IP address here. And if you want the service provider, you can just type service provider instead of data center, and you can just check for DCBX configuration. In this case, as you can see, we can just configure different types of priorities. For example, 2, 3, 4, all of them for SAN traffic, and then go for validation. And also, if you go down, you can see that for PFC parameter exchange, we have a configuration for LLDP TLV, and you can just do them in case you want to change the defaults, as a matter of fact. So I hope this has been informative for you, and see you in next videos.